Hello, my name is Hikaru Wakaura. Today, I'll talk about numerical simulation of universal and adiabatic quantum computation by time crystal, proposal of quantum time crystal computing. Here is my curriculum by type. I acquired doctor's degree in Teknologi on Department of Pure and Applied Sciences in Tsukuba University in Ibaraki at 2017. I have studied for application of spin vortex induced current at qubits. It is non-size loop percent loop current on qubit conductivity. Here is my job experience. From now on, I am private scientist and I am looking for next research job and opportunity. It is brief topic of my presentation. Since Professor Richard P. Feynman has proposed the formidability of quantum computing, many kinds of quantum computing have been proposed. For example, universal quantum computing, quantum annealing, quantum computing, one-directional quantum computing, variational quantum algorithms, quantum reservoir computing, etc. Here is a list of quantum computing methods for resilience of noises. Universal quantum computing is very promising because some universal quantum algorithms can solve some problems in polynomial time that classical computers can only solve in exponential time. Circuit is universal, but any kind of noises are very harmful. Universal quantum computers have architecture that avoid noise at a maximum. Variational quantum algorithm is hybrid algorithm of universal quantum computing and classical optimizer. Circuit is limited by noise to avoid phase kick. And thermal and voltage rotation are still harmful. And there are other quantum computing. It is the method of quantum computing that uses time propagation of the quantum system, such as quantum simulation. Then, there has no such, and Hamiltonian is universal, and Hamiltonian changes gradually from initial to final. And it is robust for thermal noise. But other types of noises are still a little harmful. Quantum annealing is one of quantum computing methods. Professor Nishimori has proposed. It uses the coherence of initial quantum sets to calculation. Hence, it has no such, and Hamiltonian is limited. And some it is still a little weak for thermal noises, but other types of noises are all no effect. Quantum crystal computing it presents today is the novel quantum computing method to use time crystals for computing. Time crystals propagate by the rotational noise. Hence, it is promised that robust for rotational noise. But the effect of other noises are unknown. It has no such, and Hamilton is universal. Time crystal is universal phenomenon of many body localization in quantum systems. This phenomenon prolongs the lifetime of quantum coherence 10 times or more. For example, the group at Aalto University announced that time crystals could be used as cubics. They have a long lifetime above 2 seconds after the crossing of energy level. This is a picture of time crystal. Time crystal states emerge in quantum systems driven by electromagnetic fields called Floquet systems. It is a Hamiltonian or Floquet system. It is periodically with the phase is the period of two large things. At the area of period, the system is irradiated by Pauli X pulse. All qubits are flipped. And the Hamiltonian is driven by noisy fields at later half period. It is an example of noisy Hamiltonian. It is noisy parameter, and the Hamiltonian is the form of Gibbs Hamiltonian. Then, blue circle indicates the qubit is in 0 state, and red circle indicates qubit is in 1 state. If time reversal symmetry is destroyed, time crystal phase is destroyed. So for example, gate operation, measurement, etc. Time crystal prolongs the lifetime of quantum coherence. Also, time crystal is destroyed by the operation breaks time reversal symmetry. Controlling noise can control the state of time crystal. Therefore, we propose a novel method of quantum calculation that takes advantage of time crystal. We call this quantum time crystal computing. So now, I'll talk about the details of quantum time crystal computing. Quantum time crystal computing performs given calculations by introducing the appropriate noise Hamiltonians on the system. Then, n is the number of qubits, and h1 includes the noises, and d is assumed tunable coefficient, which is 0.01 for all calculations. This noise parameter is the sum of constant term and noisy term. It is constant term and this noisy term. Noisy term is random number that the probability of the value is expressed as the Gaussian, by the Gaussian. And parameter is expressed from the value from here to here. Both constant term and noisy term has a realm from -2 to +2. And entire realm is from -4 to +4. It is a deformated flowchart of time crystal quantum computing. At first, system is initialized and propagated by time crystal. And at a given time, probability distribution for the state is read out. And by this, loss function is calculated. If the system is converged, calculation stops. Otherwise, parameters are modified by optimizer, and calculation is repeated from scratch by this modified parameter. And practical calculation of quantum time crystal computing of time propagation is performed with the optimized parameter. Then, parameters are optimized in the manner of Born massive. So, loss function is these two, this MMD loss function and Karlbach divergence like loss function. で、small f indicates probability distribution for the state. And fa is the aimed distribution. で、kernel is K, it's Gaussian. We use covariance matrix adaptation evolutionary method summarized as optimizer. Optimizers must deal with noisy parameters. Ordinary optimizer, like cross-Newtonian method, cannot optimize them. Meta-heuristic optimizer are needed. For example, Thomas method, data optimization, and genetic algorithm. Simulator is Floquet SDK. It is simulator of quantum calculation. Number of shots per trial is infinite. It is a research for universal quantum computing. First, it is research of rebound from zero state to zero state. It is loss functions values for number of iterations. Blue line indicates the average of loss functions for the 10 attempts of calculating loss functions. Orange line indicates the median. Blue area indicates the real of loss function. And green hat area indicates the standard deviation of loss function from average. It is a result of time propagation by the base parameter. Then, it took those functions at t equals 4 at t. So, at t equals 4 at t, zero state is rebounded correctly. And from then, rebound continues. This is the result for making every distributed state from zero state. Then, probability then, those functions value is looks not so good, but probability distribution is made correctly because the end state form is simple. So started from zero state and every distributed state is made correctly at t equals 4 at t. Simple gate operations can be emulated using quantum time crystal computing. Then we try to emulate universal quantum computing algorithm. First, we try to make global operator in zero state. Global algorithm is certain algorithm that given state by repeating oracle operator and global operator. The variable function is not bad, but calculation of probability distribution failed. At the aimed case, the probability distribution at t equals to t must be 0.35, but it is not fit. And we try this using other Hamiltonian. It is a result of I think Hamiltonian. Those functions value is worse than above, and probability distribution and time propagation is failed. It is a result for one body X and Z Fourier operator. the probability loss function's value is the smallest, but phase. And we try to making Oracle operator and zero states by shadow tomography. Shadow tomography is the method to express the phase. You can optimize the phase, but the value of loss function is nearly 80 in average. And time propagation is phase. For ideal case, the probability says the phase of zero state must be 1, but not it. It is a result of quantum Fourier transformation by the manner of subdistance variation and quantum solver. Then, that indicates the phase. That indicates the period of the wave that is transformed by quantum Fourier transformation. T equals 16, equating are both phase. Simple gate operations can be achieved, but universal quantum algorithms have been performed correctly. Fixed value of noises have limits of propagation. Changing noise parameters may appear. It is the result of the paper on Professor M.P. Estrada's. If this epsilon means the parameter of time Floquet Hamiltonian on time crystal. The changing epsilon, the result of time propagation, differs drastically. Hence, changing noise parameters may contribute to noise, to accuracy. We perform this Adiabatic quantum computation. We perform Adiabatic quantum computation by time crystal computing the following noise Hamiltonian changes statistical. For X bar is 10, but and noisy Hamiltonian driven by noisy field changes gradually from initial to final. It is an example for Adiabatic Groverâ's algorithm. And result of Groverâ's algorithm aiming zero step is here. The value of loss function is lowered by the number of trials. This is the base value. It means the aim state is derived correctly. It is the result of time propagation for base parameter. Result of Groverâ's algorithm is performed correctly. Zero state it only appears at final, and the phase is 1. Hence, it's correct. Result of Shorâ's algorithm we performed 2. Shorâ's algorithm is famous algorithm, quantum algorithm that factorize given integer. We performed factorizing 21 into 7 and 3. But this Hamiltonian. Result of Shorâ's algorithm is this. This is the base parameter. It means same set is derived correctly. If the aimed case, state 7 is only appears at the final. Then it is succeed. Even parameters are noisy. Adiabatic quantum computation is achieved accurately. Changing noise parameters may contribute to accuracy. Here is discussion. Evenly distributed states is difficult to the initial state of number state. Conclusion. Universal quantum algorithms haven't been performed correctly. However, Adiabatic quantum computation is achieved accurately. Quantum time crystal computing is practical on arithmetic quantum computation has potential to be practical on universal quantum computing. X and DXD pairs exist as noisy. Hence, quantum time crystal computing is plausible in nature. Future plan is to establish the methods to perform universal quantum computation accurately, and machine learning by the manner of recurrent neural network, quantum reservoir computing, and variational quantum called Morano-Arnold network. Starting natural quantum time crystal computing computers is also. It is an example of machine learning using quantum time crystal computing with neural network. That's all for today. Thank you for hearing.